Assalamualaikum warahmatullahi ta'ala wabarakatuh. Okay, and very good day to everyone. Alright, so basically, uh, today we still on topics fundamentals of thermodynamics, but in different topic, which is focusing on air standard cycle. So part 1, the topic is on the content is on reciprocating engines. Okay, so introduction to power cycle. So two important areas of application of thermodynamics are power generation and refrigeration. The device or system used to produce a net power output are often called engines, and the thermodynamic cycle they operate on are called power cycle. So basically in your syllabus we focus on power generation, but refrigeration will be taught in thermal engineering, MEC 551. Okay, so in this syllabus we focus on power generation. Alright, so thermodynamic cycles can be divided into three categories. One, we call it as a gas or vapor cycles. So gas cycle is a working fluid remains in the gaseous phase throughout the entire cycle. And vapor cycle, where your working fluid exists in the vapor phase during one part of the cycle and in the liquid phase during another part. 2. Closed or open cycle. Closed cycle. The working fluid is returned to the initial state at the end of the cycle and is recirculated. And for open cycle, the fluid is renewed at the end of each cycle instead of being recirculated. So number 3, we have internal or external combustion engine. So external combustion engine, heat is supplied to the working fluid from an external source. For internal combustion engine, heat is supplied by burning the fuel within the system boundaries. In general, thermodynamic cycles are complex. Therefore, various gas power cycles are analyzed under some simplification. Okay, so this is the hierarchy for power cycle. So firstly we have heat engine. So heat engine divided into two. First we call it as a external combustion, and two is internal combustion. So for external combustion is steam engine, and this topic we will discuss on chapter 6, next chapter. For this chapter we focusing on internal combustion. So internal combustion, we have three types. First we call it as a reciprocating, two we call it as a Wankel, and lastly rotary gas turbine. So in this chapter we focus on reciprocating. So reciprocating, we have two types, CI and SI. CI SI is spark ignition, CI is compression ignition engine. So compression ignition normally focusing on diesel engine. So for spark ignition normally is for petrol engine. Okay, so CI engine we have two types, 2-stroke and 4-stroke. Same with SI engine, we have 2-stroke and 4-stroke. Okay, so in this in your syllabus we focus on CI and SI, compression ignition and spark ignition. So basic consideration in the analysis of power cycles. The cycles encountered in actual device are difficult to analyze because of the presence of complicating effects such as friction and the absence of sufficient time for establishment of the equilibrium during the cycle. Because the cycle is very fast, so basically the device to record that cycle is not efficient. So to make an analytical study of a cycle feasible, we have to keep the complexities at a manageable level and utilize some idealizations. This is called modeling the cycle. So if a cycle resembles the actual cycle closely but is made up totally of internally reversible process, it is called ideal cycle. The ideal cycles are internally reversible, but unlike the Carnot cycle, they are not necessarily externally reversible. Therefore, the thermal efficiency of an ideal cycle in general is less than that of a totally reversible cycle operating between the same temperature limits. However, it is still considerably higher than the thermal efficiency of an actual cycle because of the idealization utilized. The cycles discussed in this chapter are somewhat idealized, but they still retain the general characteristic of the actual cycle they represent. Okay, so basically, as in this figure, so we have a PV diagram. So you can see that the dotted green line is actual cycle. So in our consideration, we are calculating using the ideal cycle in a red line. Alright, so normal efficiency of a heat engine is work net produced by the engine divided by Q in, heat in. Okay, alright, so the idealization and simplification in the analysis of power cycles can be summarized as follows. The cycle does not involve any friction. We assume is a frictionless. Therefore, the working fluid does not experience any pressure drop as it flows in pipes or devices such as heat exchanger. All expansion and compression process take place in a quasi-equilibrium manner. Normally, in reality, it's in the transient condition. But in this consideration, we assume it's in the equilibrium condition. So number 3, the pipes connecting the various components of a system are well insulated, which means that no heat transfer through and go in, go out, and the total heat transfer is negligible. Okay, so neglecting the change in kinetic and potential energy of the working fluid is another common utilized simplification due to devices that involve shaft work such as turbines, compressors, pump. Okay, and the kinetic and potential energy terms are usually very small relative to the other terms in the energy equation. So the only device where the change in kinetic energy are significant are the nozzle and diffuser, which are specially designed to create large change in velocities. So the property diagram such as PV diagram and TS diagram have served as valuable aids in the analysis, whereby the area enclosed by the process curve of a cycle represent the net work produced during the cycle. So basically, if you have seen this diagram, PV diagram, so this area is your work net. Same with TS diagram. So within this area is your total work net. Carnot cycle. The Carnot cycle is composed of four totally reversible process. First, we call it as a isothermal heat addition. Number 2, isentropic expansion. Number 3, isothermal heat rejection. And lastly, isentropic compression. For both ideal and actual cycle, thermal efficiency increase with an increase in the average temperature at which heat is supplied to the system, or with a decrease in the average temperature at which heat is rejected from the system. So basically, consider a steady flow Carnot engine. So 1 to 2 is a isothermal heat addition. Okay. Number 2 to 3 is a isentropic heat rejected. Okay. 3 to 4 isentropic for turbine heat, whereby your work net is produced. Okay. And 3 to 4 heat being rejected, and it's isothermal. Okay, isothermal heat rejection. And lastly, isentropic compression. Okay, so basically compression process goes in compressor, and turbine is isentropic expansion. Okay, so if we consider the PV and TS diagram, so this is your diagram. This is a PV diagram, and this is for TS diagram. Okay, so for TS diagram, so if we consider TS diagram, so point 1 to point 2, the same temperature. Process 2 to 3 is isentropic, same entropy. 3 to 4, same temperature, heat rejected at same temperature, isothermal. So 4 to 1 also isentropic. This 4 to 1 process is a vertical straight line. Okay. So the Carnot cycle was introduced as the most efficient heat engine that operate between two fixed temperature. We have TH high and T low, TL low. The thermal efficiency of Carnot cycle is given by 1 minus T low divided by T high, temperature at high temperature. Okay, so upon the derivation of the performance of the real cycle is often measured in terms of its thermal efficiency. Okay, so basically we have efficiency is work net divided by Q in. So work net is come from Q in minus Q out. So Q in minus Q out, substitute into this equation with net. So we have Q in per Q in, we have 1. So we have 1 minus Q out per Q in. As your Q out, this is your Q out. Okay, process from process 3 to 4, we have Q is the same with process isentropic process 3 to 4 and 2 to 1. So the difference is only based on the temperature. So the point is the same. Let's see the vertical condition. So the difference is only by temperature. As standard assumption, in power engine, energy or heat is provided by burning fuel within the system boundaries. For example, internal combustion engine, jet engine, and etc. The following assumptions are commonly known as the air standard assumption. Firstly, the working fluid is air, which continuously circulates in a closed loop and always behave as an ideal gas. So we assume that the air is in ideal gas condition. So number 2, all the process that makes up the cycle are internally reversible. Number 3, the combustion process is replaced by a heat addition process from an external source. Normally, this process, okay, is heat being addition. Heat addition is come from the combustion. So we assume in this section that the heat being supplied. Number 4, the exhaust process is replaced by a heat rejection process that restore the working fluid to its initial state. Okay, so basically this exhaust process is we assume as a heat rejection. Okay, so cold air standard assumption. When the working fluid is considered to be air with constant specific heat at room temperature 27 degrees Celsius or 300 Kelvin, so we have your CP, specific heat at constant pressure 1.005, and specific heat at constant volume 0.718, where and your K is we assume at 1.4. So air standard cycle is a cycle for which the air standard assumption are applicable. Okay, so overview of reciprocating engines. A reciprocating engine is an engine that uses one or more piston in order to convert pressure into a rotational motion. They use the reciprocating up and down motion of the piston to translate this energy. So this is the movement of this piston, we call it as a reciprocating. So this is your engine. So in engine we have a cylinder head. In cylinder head also we have a valve, intake valve and exhaust valve. So intake valve is used to transfer fuel and air inside the combustion chamber. So this is your combustion chamber. So this is your piston. Okay, so the fire come from spark plug. So this is for spark ignition. Petrol. For diesel, we don't use spark plug. It based on the pressure. So at the bottom we have the connecting rod. The connecting rod is used to connect the piston with the crankshaft. So this is the 4-cylinder reciprocating engine. So overview of reciprocating engine. So the reciprocating engine is one of the most common machine that is being used in a wide variety of applications, from automobiles to aircraft and also to ship. It is actually a piston cylinder device where piston moving back and forth inside the cylinder to convert heat into a work. The nomenclature for reciprocating engine includes the top dead center, TDC. Top dead center is the position of the piston when it forms the smallest volume in the cylinder. So that is, we call it as the maximum displace. The maximum piston can go forth. So that we call it as a TDC. The minimum piston go backward, we call it as a BDC, bottom dead center. Okay, the stroke is the distance of the piston travel in one direction. So from TBC to TDC is your stroke. The length we call it as a stroke. From TDC, the piston movement from TDC to BDC, we call it as a stroke. The bore Bore is the diameter of the cylinder block, or sometimes we acknowledge from the diameter of the piston. The clearance volume VC, the minimum volume formed in the cylinder when the piston is at TDC, known also as the volume at TDC. So TDC is this portion whereby your piston is at maximum. So we have some volume left out here. Okay, so this volume we call it as a clearance volume. Displacement volume is the volume displayed by the piston as it moves between the TDC to BDC. So from TDC to BDC is your volume of displacement, VD. Okay, so normally we have how to calculate the displacement volume VD. We use this formula. So B is your bore diameter or piston diameter or cylinder block diameter times your length. Length is your stroke. We have a volume. Compression ratio, the ratio of maximum to minimum clearance volume in the cylinder. So normally Vmax and Vmin, we will see this figure is in PV diagram, but in reality Vmax, we have this Vmax is Vc plus Vd divided by Vc. I repeat again, the Vmax normally form Vd plus Vc divided by Vc. That we have a compression ratio. Mean effective pressure, MEP, a frictious constant throughout the cycle, a frictious pressure that if acted on the piston will produce the work. An engine with higher MEP will produce a larger net output work. So MEP is your work net divided by Vmax minus Vmin. So Vmax we can determine from PV diagram, and also Vmin also we can determine from PV diagram. Okay, so the mean effective pressure can be used as a parameter to compare the performance of reciprocating engine of equal size. The engine with a larger value of MEP deliver more network per cycle and thus perform better. Introduction to petrol engine. A petrol engine, known also as gasoline engine in American English, is an internal combustion engine with spark ignition, SI engine, okay, and designed to run on petrol or gasoline and similar volatile fuels. The first practical petrol engine was built in 1876 in Germany by Nicolaus August Otto. Although there had been earlier attempts by Etienne Linnell, C. Griffith, Siegfried Marcus, and Julius Hoch, and George Brayton. The first petrol combustion engine, one cylinder, 121.6 centimeter cube displacement, was prototyped in 1882 in Italy by Enrico Bernardi. In most petrol engines, the fuel and air are usually pre-mixed before compression, although some modern petrol engines now use cylinder direct petrol injection, GDI, gasoline direct injection. Okay, So the pre-mixing was formerly done in a carburetor, but now it's done by electronically controlled fuel injection, except in small engine where the cost or the complication of electronics does not justify the added engine efficiency. Four-stroke spark ignition engine. So a four-stroke engine, also known as four-cycle, is an internal combustion engine in which the piston completes four separate strokes while turning a crankshaft. A stroke refers to the full travel of the piston along the cylinder in either direction. Okay, so the four separated strokes are termed firstly intake, known as induction stroke or intake stroke. Okay, so the piston begin from TDC, top dead center, and end at BDC, bottom dead center. The compression stroke. This stroke begin at BDC or just at the end of the suction stroke and at the end of the TDC. The piston compress the air-fuel mixture. Both the intake and exhaust valve are closed during this stage. Combustion, also known as power or ignition, this is the start of the second revolution of the four-stroke cycles. The piston is at TDC, okay, the end of the compression stroke. The compressed air-fuel mixture is ignited by a spark plug, forcefully returning the piston to BDC, bottom dead center. This stroke produces mechanical work from the engine to turn the crankshaft. Exhaust stroke, also known as outlet stroke, the piston once again returns from BDC to TDC while the exhaust valve is open. This action expels the spent air-fuel mixture through the exhaust valve. Okay, so firstly we look into this diagram. So firstly we determine the intake stroke. Okay, first this is called intake stroke, compression stroke. Okay, alright, so this is first stroke. Okay, so the blue one is intake stroke, whereby your air-fuel ratio enters the combustion from the piston movement, and then the piston is compressed. See, this is the compressed, number 2. Okay, from this compression, and then we have the spark plug. So you see the fire there, that is the spark plug. So the air and fuel being burned inside the combustion chamber. Okay, and lastly the chocolate one, that is, we call it as the exhaust gas. So in the last cycle, the exhaust valve will open and the exhaust gas will be released in the exhaust. Okay, so this is the example for four-stroke engine, 4-cylinder, normally inside the car, or a superbike engine. Okay, so we have a 4-piston movement. Okay, so this we call it as a inline 4, as the piston is in inline. Also, we have another engine configuration. We have a V-twin, whereby your piston is V. Okay, we have also flat 4. Okay, so basically normally flat 4 other may call it as a boxer engine. Okay, so V6, very popular in Malaysia for Perdana V6. Okay, we have 6 piston, 3 in a row, and other row we have 3 piston. And lastly, V8 engine. Okay, 4 piston in a row, and other part is 4 piston. Alright, 4-stroke spark ignition engine. So this is the intake stroke, whereby your intake valve will open and the air fuel mixture will goes in. So this is the suction made by the piston goes down. Okay, as the crankshaft rotate, so the mixture will be forced to compress, and the valve is both being shut down. Okay, so at the top, as the piston move to the top TDC, so the maximum condition, so the spark plug will firing, that makes the piston move towards the bottom BDC. Okay, as the crankshaft rotates after the BDC, piston also move again to the top, and the exhaust valve will open, releasing the mixture of burnt gases into the exhaust. So we have ideal cycle for spark ignition engine. We call it as a Otto cycle. Okay, so in this consideration, this is the actual condition. So starting from intake, okay, intake condition, so and then compress, okay, compression, okay, and then the power start to ignite, spark plug, okay, and then expand, the piston move downwards. Okay, so this expansion, the valve is open, exhaust valve is open, okay, and the gas is released. Okay, so in this actual condition, the ideal condition, so we remove out the exhaust and intake condition. Okay, we are only concentrated on isentropic condition, whereby the piston compress the air inside the combustion chamber. Okay, so this is the condition whereby the piston from BDC to TDC compress the air fuel mixture, and then heat being supplied, where the spark plug ignite. Okay, ignite, so the pressure will goes up, and then after the combustion, so the piston goes down, moving the crankshaft. Okay, and at the bottom, the valve, exhaust valve will start to open and releasing the burn gas. So we assume that is in the heat being rejected to the exhaust. Okay, so this is the PV diagram for Otto cycle. So ideal Otto cycle. So air enter the cylinder through the open intake valve at atmospheric pressure during the 0 to 1 process. So this normally we left out, okay, because it's a constant pressure process. Normally we neglect this process, so we focusing on starting from point 1. So the point 1 is intake valve close, and it's compressed isentropically to point number 2, and then from point 2 the heat being injected, or the combustion process occurs, so increasing the pressure inside the combustion chamber, and then it expand isentropically after the combustion, expand isentropically to point 4 as the piston move down to BDC. Point 4 is the bottom. This is your TDC, this is your BDC. Okay, and then the 4 to 1 heat being rejected to environment. This process we call it as a heat being rejected. Okay, so the process of Otto cycle is as per following. This process 1, 2, we call it as a isentropic compression. process 2-3, we call it as a constant volume heat addition. Process 3-4, isentropic expansion, and process 4-1, constant volume heat rejection. So this is the diagram for PV diagram, and this is for TS diagram. Normally for Otto cycle, we use PV diagram, as we know what is the pressure and what is the volume inside the combustion chamber. Okay, the related formula. Recall back in chapter 3 and chapter 4, we have determined what is the isentropic process. So process 1-2 is a isentropic compression. So this is your formula related to the process. So process 2 is a constant volume heat addition. Constant volume. Okay, so we use a CV. So this is your mass. Normally we use a m dot. Okay, so if this m dot kg per second, so the output, the heat here is in watt. Okay, so as we only use a mass, not m dot, not mass flow rate, so the unit here is only joule. Okay, so please be aware to these units. Okay, process 3-4 is a isentropic expansion. So this is the formula related with the isentropic expansion. So this has been introduced to you in chapter 4. Okay, so for process 4-1, constant volume heat rejection. So same with process 2-3. Okay, so we got the Q out. So thermal efficiency of the Otto cycle. So in general, the efficiency of cycle can be determined by using the work net divided by Q in. Work net divided by Q in. So work net is Q in minus Q out. So from these equations, we can cut in. So we have final equation. Okay, so to apply first law to process 2 and 3, as your volume is constant, okay, so your pressure, okay, your constant specific heat, so we got this condition whereby your Q in also, this is from combustion chamber, mass of fuel times the calorific value is the same with the mass heat being ejected. So mass times calorific value is same with mass times constant specific heat at constant volume times different temperature. So this is same with this. Okay, for process 4-1, heat being rejected. Okay, so also similar. Okay, so the thermal efficiency, we can substitute Q in and Q out inside the thermal efficiency. So finally we got this value from the temperature. Okay, we can cancel out. So we got this. Okay, so rearrange, and as process 1, 2, and 3, 4 are isentropic, so we can replace the volume with temperature, and finally we have 1 minus T2 T1 divided by T2, and this temperature ratio can be substituted by volume, and this volume is a compression ratio. Okay, so BDC, TDC, this is the specific volume. Okay, so this specific value, this is your maximum, this is your minimum value, minimum volume. So if you want to calculate the compression ratio, so this volume divided by this volume. Okay, so that's why we have this figure. So finally, the efficiency of Otto cycle, we have 1 minus 1 divided by R K minus 1. Okay, sample problem 5.1. Okay, example sample problem 5.1. Calculate the ideal air standard cycle efficiency based on the Otto cycle for a petrol engine with a cylinder bore of 50 mm, a stroke of 75 mm, and a clearance volume of 21.3 centimeter cubic. Okay, so sample problem 5.1. Okay, so given in the exercise is cylinder bore. Okay, cylinder bore. Okay, at 50 mm. Okay, so basically is a 5 centimeter. Okay, and stroke. Okay, stroke is at 75 mm, which is 7.5 centimeter. Okay, and clearance volume is 21.3 centimeter cubic. Okay, so the question is to find the efficiency, cycle efficiency. Okay, so here what we should know is that we need to draw a, for further understanding, we need to draw a diagram. Okay, for example, so this is your clearance volume, cylinder head. For example, this is your motorcycle, so this is your spark plug. Okay, alright, so this portion we call it as a clearance volume. So clearance volume VC. Okay, alright, and below that is your cylinder block. Okay, so let's say for example this is your piston. Okay, piston pin. So this is your TDC. Okay, so the bottom part, let's say for example if your piston moving down, so this is your BDC, bottom dead center, top dead center. Okay, so this is your stroke. Okay, stroke. Alright, so from here we can determine what is your, so this area, this area is your VD. VD is your volume of diameter inside here. Okay, so for this is the, what you call it as a petrol engine. So petrol engine use a Otto cycle. Okay, so basically the efficiency is 1 minus 1 over R. This is a compression ratio, R compression ratio, K minus 1. Okay, and given K is 1.4 for adiabatic. We assume that here no heat being lost, so it's a adiabatic. Okay, alright, so in order to determine your compression ratio RC, okay, so bear in mind compression ratio is VD plus VC over VC. Okay, so this is your VC. VC is being given directly. Okay, so we need to determine what is the VD. So VD is pi, okay, pi D, diameter of the cylinder bore, 50 mm. So we got 5 centimeter. Okay, same unit. So basically 5/2. Okay, by 4. So you can get your VD centimeter. Okay, right. So we have the area. This is your area. Okay, so we need to times. Okay, so this is area, so you need to times. Okay, so we erase first. Okay, so we need to times the stroke. Okay, stroke is at 7.5. Okay, so we got your answer is in centimeter cubic. Okay, alright, so we got VD, VC. VC is given directly, VD can be calculated here. Okay, so the efficiency, okay, is alright. So we can get something. So times 100. Okay, times 100%. So we can get your in percentage. Okay, right. Thank you.